everyone. Good evening, and welcome to the 5th Annual Neekeyfar Lecture on Science and Mathematics. This is hosted by the Student Advisory Board for Science and the Office of the FAS Dean of Science. My name is Anna Zhao, and I'm a sophomore, currently concentrating in HDRB. This is my second year as a member of the Student Advisory Board for Science, and I'm so excited to be a part of this event. On behalf of the board, I would like to thank the Office of the Dean of Science for helping us to make this lecture series possible. Thanks to the generous donations and contributions of an anonymous donor, we have been able to invite prominent scientists and mathematicians to share their passions and experiences here at Harvard. This is already our 5th lecture, and we hope to promote a long tradition of Neekeyfar lectures and events that offer undergraduates the opportunity to interact with these scientists and mathematicians who are at the forefront of their fields. We live in a thrilling time of scientific innovation and discovery, as breakthroughs in all fields expand to resonate across society, and we hope to bring these discoveries to Harvard through this lecture series. The distinction between science fiction and nonfiction continues to be blurred in the continuous progression of science. And tonight's speaker has made discoveries that truly seem to be an invention of science fiction, venturing beyond our own solar system in his research. So without further ado, I am honored to welcome Professor John Asher Johnson as this year's speaker. Professor Johnson is a professor of astronomy here at Harvard, coming here to us from Caltech just this past year to join Harvard's ever-growing family. As a professor of astronomy and a former researcher with NASA's Exoplanet Science Research Institute at Caltech, Professor Johnson has made extraordinary discoveries in his field. This past year, he and his team discovered not one, but 3 exoplanets orbiting a red dwarf, one of which is the smallest exoplanet found to date. His discoveries in the field, originating from when he was just a grad student, have resulted in the establishment of the EXO Lab at Caltech and the Astronomy Learning Center at UC Berkeley, both of which are still flourishing now. Just last year, he was awarded an Alfred P. Sloan Research Fellowship, as well as the Richard P. Feynman Prize for Excellence in Teaching and the American Astronomical Society Newton Lacey Pierce Prize. Professor Johnson received his Bachelor of Science in Physics from Missouri University of Science and Technology in 1999, and has since earned his master's and PhD in astrophysics at UC Berkeley, both of which, finishing his studies in 2007. He then went on to receive an NSF Astronomy and Astrophysics postdoctoral fellowship, working at the University of Hawaii Institute for Astronomy until 2009, when he became an assistant professor of astronomy and astrophysics at Caltech. This past August 1st in fact, Harvard was able to convince him to leave sunny California and to receive a professorship here in the astronomy department. Tonight, Professor Johnson's talk will be on how one finds an exoplanet, a topic on which he is most certainly an expert. And now please join me in welcoming Professor Johnson tonight, not just as a Neekeyfar speaker, but as a member of the Harvard community.
Well, thank you very much for coming out tonight and hearing about my science. So this is the title of my talk, but it's also the title of a book that I'm working on finishing. And I'm telling you all of this to motivate myself to finish that book. I've been working on it for about a year and a half. It's been one of the biggest struggles that I've encountered as a scientist, and it's also been quite enjoyable as a result. And so the structure of this talk follows the structure of that book, and I hope that inspires you to buy a copy when it's ready. So let's go ahead and start out with the origins. But first of all, let me just give you an introduction myself. I'm an exoplanetary scientist. It's a brand new field that's only been around for less than 20 years. And the science, exoplanetary science is the study of planets around stars other than the sun. And the origins of my story in this field began in Missouri, as you heard from the introduction. I actually grew up in St. Louis, Missouri, which is up here. And some of the features of the beautiful city of St. Louis are its gigantic stainless steel arch, its beautiful skyline along the river, and the fact that there is a lot of light pollution in St. Louis, just like there is in most major cities. That combined with the extremely hot temperatures in the summer and the very, very cold temperatures in the winter are part of the reasons I think I didn't see the night sky or take much note of the night sky until I was about 20 or 21 years old. For my view of the night sky and to really start taking inventory about what's up there, I had to wait until I was in university. I went to the Missouri University of Science and Technology in Rolla, Missouri, which is about 100 miles down the road from St. Louis. It's a tiny town of about 14,000 people, about 8,000 people during the summer. And while working at Rolla on my physics degree, I also worked at the radio station, 89.7 KMNR. And there was a public service announcement one week about a meteor shower that was predicted to happen a few nights later in the week. And so my friend Jason and I decided to round up a few friends, grab some blankets, and drive out to just outside of Rolla, Missouri, to a farmer's field. And there we were able to enjoy very dark skies. And we looked up and we saw a gorgeous meteor shower. These are the Leonids. And as we sat there contemplating rocks burning up in the atmosphere, we also started noticing, as our eyes adjusted, this swath of light across the night sky. And we started talking about what it was that we were seeing. And it became clear to us that we were actually seeing the inside of our galaxy. We are in a flattened distribution of stars, and there are about 200 billion stars in the galaxy, and we're in the outer edge of that flattened distribution. And so as we were looking out, we were actually seeing through the disk of the galaxy. As we looked up and away from the galaxy, which is actually kind of left in this image and left in our sky, we were looking up and out of the plane. And it was getting this sense that we were orbiting a planet situated sort of sideways in the galaxy. It gave me my first sense of where I was in the universe. And then we started talking about the stars. And from that night on, I started taking note of the night sky. I kind of started looking up for the first time in my life. One night I looked up and I saw a scene not too different from this. This is actually in Iran. This is a beautiful picture that was on the astronomy picture of the day. But what I saw was something similar to this. I saw the moon hanging in the sky, and I saw two bright lights. If I remember properly, Venus was down here, and there was another bright light further up. And I had heard that that was Venus before, but I was unfamiliar with the other very bright light. And so I asked Professor Schmidt in my physics department, who knew something about astronomy, and expected him to give me the name, some Latin name for some star or something up there. And he told me that it was actually Jupiter. And I thought, oh, wow, that's really cool. And I remember also thinking about how all of these things line up in our night sky. You can kind of trace an arc across the sky. And that's the ecliptic plane, the plane in which all the planets in the solar system, well, most of the planets in the solar system orbit within. And then again, I got that sense of sitting sideways on the side of the Earth, looking out across the plane of our solar system. Also, Jupiter is kind of my first planet discovery. Okay, well, people had already found it before, but it was new to me, and it was a real true discovery to figure out what it was. So the night sky, if you stand there watching long enough, or if you have a camera set up, you'll see it rotate from east to west slowly throughout the night. And from night to night, the stars basically remain pretty much fixed with respect to one another. And it's this view of the sky, if this was all there was to it, I would think that science would have had a much later start in human history. But it's not just the stars that are up there doing their very predictable motion, swinging from one side of the sky to the next. But I'll get to that in just a second. But this is the view that ancient people, going back through the ages, have contemplated and wondered about. And this led to Greek philosophers to come up with what's now known as the two-sphere model of the universe. The basic idea is that we are standing on one of those spheres, the Earth, and even the ancient Greeks knew that we were standing on a spherical Earth. They didn't believe in a flat Earth. And they believed that what we were looking up and seeing was the inside of a second sphere. And on that sphere, or in that sphere set into it, were the stars. And it was that sphere that was rotating around the center of the universe, where the Earth lied. And that was it. That was the whole conception of the universe. Our sphere that we're on, and that other sphere out there holding the stars. Well, there's a little bit more to it. They believed in the 5 classical elements, and they believed that these things were situated within the universe, ordered by roughly their weight, and the heaviest stuff tended towards the middle. And this is why we feel ourselves pulled towards the center of the Earth. They felt like we were made out of the heavier stuff, and we were kind of held here. And it was also down here where all the heavy stuff was, is where all their attention was turned. This is where all of the affairs of man took place. And it was up here that was pretty much outside of our reach. Furthermore, the things that were up there were part of the heavens. And they were perfect and unchanging, had always been and would always be. Everything moved on perfect circular paths, and so they looped back onto one another after the year went by or after the night goes by. And it was this perfect circular eternal motion that was attributed to the sky. And up there in that aether, it was perfect, unblemished. Down here on the earth, it was imperfect and changing. And this is where the concerns of man were. And this is where most of the philosophy was concerned with. It was what was going on down here at earth. Really, it was fairly uninteresting up there. It was pretty, and the positions of things could maybe help judge your horoscope or predict your horoscope and things like that. You can make predictions about how your day might go. But as for the exact nature of those things that were up there on that other sphere, because they were eternal and perfect and unchanging, it wasn't really worth asking, where do they come from and how does it all work? Except for the planets. If you look up in the night sky with respect to the constellations, you'll see the planets moving mostly from east to west. But Mars and Jupiter and Saturn are the iconoclasts of the sky, and they occasionally like to reverse their path and then loop back around throughout the year. And it's this retrograde motion that really throws a wrench in the works for that old hypothesis of a two-sphere model. Now you need other spheres. You need to hold the planets in their motion. And so really the two-sphere model refers to those spheres that are up in the sky and the one that we live on. But to account for this retrograde motion, there needed to be yet another modification. And that other modification was the idea that the planets, specifically Mars and Jupiter and Saturn, moved on epicycles, and Venus and Mercury as well on more complicated epicycles. But these are basically circles riding on top of circles. And as this smaller circle rotates along its orbital path, you occasionally get a reversal of motion. But this doesn't really quite work because you need to tune this so that this epicyclic motion happens at specific times. And in order for this to be a very useful, practical, predictive model, you have to break from the notion of uniform motion for the planets. Either that, or you just have to just kind of wave it away and just say, oh, it's basically still circles. They're basically still perfect. This whole notion didn't sit very well with Nicholas Copernicus. He did many things. He did medicine, he did politics, he did theology, but he also did a lot of astronomy. And he really wanted things to fit together a lot better. And he just noted that a small modification to the classical picture would account for the retrograde motion and actually provide a whole system of motion for all of the planets. And his idea was to move the center of the universe away from the Earth and move it towards the sun. And that small modification to the basic model of the universe is what really gave birth to our whole modern notion of science. It also led to a notion of the solar system. Because now you have the planets ordered such that the quickest planets are moving fast and towards the sun, and as you move out, they move slower, and this helps account for this retrograde motion. So we are moving interior to Mars's orbit, and we overtake it, and therefore it looks like Mars is going backwards for a short period of time. Venus and Mercury never stray far from the sun because they're on orbits interior to the Earth's orbit, and so they're always near the sun there. So this was a nice model because it allowed astronomers to make much better predictions for where the planets were going to be in the sky. So it had nice practical implications. The philosophical implications, people usually think that this really got the church really worked up, right? This is kind of heresy, right? Well, actually at the time of Copernicus's predictions, and after he presented his model, the church was pretty much ambivalent. They were pretty happy to have a new model for predicting where the planets were going to be. But there were a few objections. Martin Luther had raised the objection in this verse in Joshua. It said, "So the sun stood still in the midst of the heaven and hastened not to go down about a whole day." And so this implies that if it stood still on that one special day while the Israelites were slaying their enemies, that it was otherwise moving. Now, This can all be accommodated in modern astronomy because we know that the sun is moving with respect to other stars in the galaxy, so this all fits fine. But it was an objection back in the day. And the other bigger objection was, if you think of the Earth as like a cart, a horse-drawn cart, and it goes around a corner, isn't all the cargo going to fly off? So how do we stay stuck to this moving Earth? How does everything stay stuck to it? How does the atmosphere stay here? How does the moon stay in orbit around the Earth as the Earth goes around the sun? Well, without a concept of gravity, then only with this concept of heavier stuff falling towards the center, then they don't really have an explanation for why everything doesn't fly off. And so this was a major objection. Along comes Tycho Brahe. He was very dedicated to his craft. One of the things that he did was mathematics, and the other thing that he liked to do was noting the positions of things in the sky. And he was determined to improve upon the astrometric or positional measurements of the planets that had been made in ancient times and carried with them many errors. So he was determined to make much more precise measurements of the positions of the planets. He was also very passionate about math, so passionate, in fact, that he got into a dispute about a mathematical theorem with his cousin, and that dispute couldn't be solved with their mathematical expertise, so it devolved into a duel, and they got into a sword fight, and Brahe got his nose chopped off, and for most of his life he had a brass prosthetic nose. Another fun fact is that he died from a urinary tract infection because he was too polite to excuse himself from the king's court during dinner when he had to go. But Brahe's tabulated data provided the impetus for Kepler to come up with a new theory, a slight modification on the basic Copernican model. While Brahe was opposed to the heliocentric model and really liked the Earth-centric model, Kepler preferred the sun-centered model, but realized that with Brahe's data, you needed to make a modification to the orbits of the planets. You couldn't have them on perfect circular orbits. It was necessary to modify their orbits to become elliptical. And the sun was at one of the two foci of the ellipses. And so he found that the closer the planet was to the sun, the faster it moved, and the further it was away, the slower it moved, such that in an equal time interval along its orbit, it would trace out equal areas of the ellipse. So elliptical motion, equal areas in equal time, and he also came up with this proportionality relating the periods of planets and their semi-major axis away from the sun. Then Galileo comes along. Right around, he's a contemporary of Kepler's, and he didn't invent the telescope, but he was the first to turn the telescope to the night sky. And so he built his own telescope and pointed it towards the heavens. And now think back to that classical notion of a perfect, unblemished sky. It was believed that everything in that sky was also perfect and unblemished, and if it had a shape, it was also circular. Well, one of the problems was that the first thing he looked at was the moon, and it was pockmarked. It had craters all over it, far from perfect. Venus went through phases and changed noticeably in size as it went in its orbit. And this is exactly what you would predict if Venus was in an internal orbit, orbiting around the sun. You would see it go through phases as you see different parts of its illuminated face. And then he looked at Jupiter, and these are observing logs, the actual observing logs, or copies of them, I should say. And he noticed 4 little stars, attendant stars to Jupiter, that lied in a little line extending on either side of Jupiter. And they changed positions from night to night. And from taking careful note of their positions from night to night to night, he was able to discern that they were actually in orbit. They were little moons of Jupiter. And so therefore Jupiter and its satellites therefore represented a separate planetary system with Jupiter at the center. So the Earth was not the only center of motion. Furthermore, Jupiter was known to be moving throughout the universe. And if it was able to bring its moons along with it, well, there's no problem, right? You can be in motion and still have a moon. So all of this really bolstered the case for a heliocentric model of the universe. And this is known as the Copernican revolution. Some of the features of it that we carry with us today is that the Earth and humans on it do not occupy a special place within the universe. This is really important, and this undergirds a lot of, well, almost all of astronomy, certainly cosmology. There's nothing special about where we are right now. The laws of physics we now know not only operate right here in this room, but the same laws of gravitation that dictate the falling of this remote should I drop it, are the same things that dictate the orbit of stars around black holes, the orbits of galaxies around other galaxies, etc. With the sun at the center, there was now a unified solar system. There was a system of motion within the solar system, with the sun at the middle, and differing speeds of the planets depending on where they were. So now you can ascribe an ordering of the planets based on their orbital properties. This is the birth of what we now know as the solar system. It used to be the entire universe. And since the sun is a star just like billions of other stars, there might be billions of planetary systems out there in the universe. And so that's where things stood at the end of the 17th century. And right now, with the discovery of planetary systems around those stars in the night sky, we are in the process of completing this Copernican revolution. We are extending, or actually confirming, those predictions that we and our solar system are not the only things out there. And we're gaining a galactic perspective for what it is to be on a planet and where those planets come from. The sky is very much interesting. So the first method that we use to detect these exoplanets is the Doppler wobble technique. And this takes advantage of the fact that it's not strictly true to say that a planet orbits the star. Any two massive bodies actually will orbit their mutual center of mass. And the displacement away from that center of mass is dictated by the mass ratio here, right? So a small, less massive planet will cause a much more massive star to accelerate or have its velocity be much smaller than that of the planets. So the Earth in orbit around the solar system's center of mass moves at about 30 kilometers per second. And our sun, in response to the Earth's gravitational tug back on it, moves at about 9 centimeters per second. And this sort of highlights the problems involved in detecting this wobble of the central star. Planets are small, and they cause very small accelerations on their star. However, the stars are what we see. And so there's the challenge. So we can use the motion of the stars, most notably the motion of the star along our line of sight, which we can measure by measuring basically the velocity of the star along our line of sight. And we can detect this back and forth motion. Away from us, 0 velocity, towards us, 0 velocity, away from us as it goes in its orbit. To do this, we need to observe the star's spectrum. And we use what are called high-resolution spectrometers to do that. Light comes from the telescope far off over here to your right, and it enters this viewing slit. The light passes through the slit into a diverging beam, which hits a collimating mirror. That collimated beam of light comes over here, and it hits a diffraction grating, which works similar to the rainbow pattern that you see when you hold a DVD up to the light. The grooves in there can actually act like prisms and send specific colors of light into specific angles. However, the angles that come off correspond to not just lambda going into some angle, but any integer n times lambda also go off into that direction. So you get overlapping wavelengths. We then take those overlapping wavelengths and it hits another diffraction grating, and then you can split the orders out, as well as having the light dispersed in the spectral direction. And so what you end up with is an achelogram, where you go from red to less red, moving across the orders all the way up here to the upper right, where you get to blue. All of this then goes into another mirror and then focused down onto a CCD, where the spectrum is recorded, similar to the detector in your camera phone, only much larger. So this is the image that falls onto our 24 megapixel CCD. This has false color enhancement on it. It's normally just black and white intensity, where there's a mapping of wavelength to the pixel on the CCD. And these dark lines you see are indicative of this is actually a spectrum of the sun, the sunlight going into the spectrometer. And those dark lines coincide to discrete atomic transitions that are taking place in the sun's photosphere. And I see, when I look at this, you might look at this and you say, oh yeah, there's a bunch of lines, but to the trained eye, what you can see is sodium here, magnesium, this is the magnesium B triplet, there's H alpha right up there. And so these are discrete transitions in individual constituents in the sun's atmosphere. And based on the strengths of these lines, you can measure things like the temperature of the sun, the chemical composition of its atmosphere. You find out that it's mostly hydrogen and helium with trace bits of iron, which make up most of these lines. Most of these are iron transitions, as it turns out, which is why astronomers for a long time thought that the sun was made out of pure iron. But for us planet hunters, we say, oh, that's nice. That's nice that you can do all of that. But we're really interested in the exact positions of those lines. Because those happen at discrete, well-measured laboratory wavelengths that you can measure in a chemistry lab somewhere in this building, we know exactly at what wavelength these absorption lines coincide to. And if the star is moving, then those lines will be Doppler shifted, red shifted or blue shifted, depending on the motion of the sun or the star. So let's zoom in on one of those iron lines up in the yellow region of the spectrum. And here's that line falling on several pixels. And what we're measuring is the shift of that line, or really, it all comes down to just measuring the amount of light that is in each one of these pixels. Because the shift of that line is going to change the flux levels of all of these, the amount of light that's falling in each one of these pixels. Now this is all very difficult because this is hugely exaggerated. If only it were this easy. We don't see shifts this large. For a Jupiter-sized planet orbiting at 1 astronomical unit in a 1-year orbit around a sun-like star, the shift that we would be seeing is about 1/100th of one of these pixels. So there's the problem. Fortunately, we have the information about the star's motion encoded in all of these lines. And there are thousands of lines to work with. And they all have the same story to tell about the motion of the star. There are other problems, notably that little tiny CCD is on a moving platform. It's on the back end of a telescope that's vibrating. It's open to the ambient atmospheric conditions. So throughout the night, the temperature is changing, the pressure is changing. That CCD is shifting all over the place. But we have tricks to do that. What we do is we actually put a Coke can-sized cell of vaporized iodine in front of the entrance slit so that the starlight passing through it has imprinted on it the dense molecular absorption features of iodine, which we know are not, well, first of all, they're not moving. It's in this stationary cell, and we know their wavelengths exactly. So we can see this line moving with respect to that picket fence from that molecular iodine. So here is the radial velocity time series of a star that's similar to the sun, named 51 Pegasi. Each one of these data points represents a night drive up the mountain and a night spent on the telescope, where they measured the velocity of the star. And you can see that they were very busy over these days. They actually made many measurements per night. And what they saw was the characteristic back and forth motion of the star indicative of a Jupiter-sized planet. And this was very exciting. But it was also very confusing because look at the x-axis here. The period is about 4.2 days. The amplitude is consistent with a minimum mass of about half of a Jupiter mass. It's a minimum mass because you don't know the inclination angle of the planetary system. The system could be oriented like this, and you would see maximum radial velocity as the star goes around its orbit. If it's oriented like this, you have no motion of the star along your line of sight. So there's a degeneracy between the mass of the planet and the sign of this inclination angle. Keep that in mind for the future techniques I'll show you. So this is what's known as a hot Jupiter, because astronomers are very clever with our naming schemes. But it is, I mean, think about this. This is a Jupiter-sized planet, which in our solar system, Jupiter is out at 5 astronomical units and takes about 12 years to go around the sun, is instead parked right next to the star, separated by about 10 solar radii. And its year is 4.2 days. So this is pretty wacky, but then if you actually dig into the literature, back in 1952, interestingly enough, my academic great-grandfather, Otto Struve, wrote a very crazy article. And in it, he postulated that there seems to be no compelling reason why the hypothetical stellar planets should not, in some instances, be much closer to their parent stars than is the case in the solar system. It would be of interest to test whether there are such objects. Wow, nice. We know that stellar binary companions, systems of two stars, can exist at very small distances. It's not unreasonable that a planet might exist at a distance of 1/50th of an astronomical unit. Its period around the star would be about a day. We made that prediction back in 1952, 44 years before the first planet was discovered. That's pretty cool. Here's another radial velocity time series. Doesn't look much like the first one. It's not very sinusoidal. But it is very periodic, and what we've shown here is each period has been folded up on top of the first period to stack all of the velocities up. And here you see that the star is constant in its motion nearly, and then it starts moving towards us faster and faster and faster, and then poof. Then it's moving away from us suddenly, and then it slows down in its motion away from us, and then it goes very slow. What's going on there? Well, it turns out that not all planetary orbits are circular, just like Kepler predicted. And this particular exoplanet has a very comet-like elliptical orbit. This is HD 80606b. It's around another sun-like star. And here is its orbit compared to that of Mercury, Venus, and the Earth in our solar system. And this Jupiter-sized planet, it's actually about 3 times the mass of Jupiter, spends most of its time out near 1 astronomical unit, moseying along. Each one of these dots represents equal time steps. So there's Kepler's law in motion, Kepler's third law in action right there. It's hanging out there, and then for one extremely exciting week, it zips in to about 4 stellar radii, gets roasted, and then begins its journey back out into space, radiating away all of the heat that it received on its close passage. So this shows the kind of perspective that we're gaining by studying planets around other stars. We're quickly realizing, even back then in the late 90s, that planetary systems around other stars don't necessarily look like our planetary system. So along with his prediction that there should be these hot Jupiters, Otto Struve also predicted that there would, of course, be eclipses. Because if the planet is moved in very close to the star, there's a much higher geometric probability that it will transit than if it's very far away. So he predicted the next method of finding planets while he was at it, and that's seeing the shadows of planets using transits. Transits are basically the eclipses of planets. And what happens is that the planet blocks, basically it's projected into the sky as a dark circle against a bright circle, and the depth of the transit light curve is given by the ratio of the area of the planet to the area of the star. So therefore, you not only find planets using this technique, but you get to characterize them right away. Because if you know the radius of the star, then the depth also gives you the radius of the planet. And remember before that there was this ambiguity between the mass of the planet and its inclination, because you didn't know if it was like this, but if it transits, you know it's like this against the star. And therefore, any measurement of the Doppler effect for these transiting systems gives you not the minimum mass, but the true mass. And with the mass and the radius of these planets, we actually get the bulk densities, and we can start inferring what they're made out of. This technique has been used to great success by NASA's recent Kepler mission, which was launched in 2009. And the Kepler Space Telescope is a thing of beauty, especially if you like very simple astronomical units. It's beauty and simplicity. Unlike most space telescopes, which are like Swiss Army knives, if you're going to send something out to space, you might as well have it do lots of things, right? So the Hubble Space Telescope has swappable instruments and lots of different filters that can move in and out. And therefore, there's lots that can actually go wrong, too. So that's one of the downsides. But Kepler was designed to do one thing and one thing only. It was designed to look for planet transits. And so when it was launched, it went out to its Earth-trailing orbit, in an orbit around the sun a little bit further out than the Earth. And it turned its attention towards this field of view, which is about 10 degrees on a side, about the size of your 2 hands held at arm's length. And there it stared at 150,000 stars for 4 straight years, basically. Once it got there, it blew off a dust cover, and then light passes through, hits a 1-meter primary mirror, goes through some correcting optics, and then it falls onto a gigantic CCD array. Think about the one in your phone, and then look at this thing. This is the focal plane of the Kepler satellite. It's got 42 4,000 by 2,000 pixel CCDs. And on that field of view lie all of the target stars that Kepler ever looked at. Now, before I show you the data that come from Kepler, I want to just kind of calibrate your mind so you can maybe have them blown away. These are data taken from a 1-meter telescope on the ground when I was in graduate school, at my last year of graduate school. And this was back before we had space telescopes routinely making these types of measurements. And we were very, very proud of these 2 light curves taken with 2 smallish telescopes. The scatter about the mean, or the model here, is about 1,000 parts per million. Strange measurement, yeah, but it's about 0.1%, all right? So that's the precision that you can get from the ground. You can't do a whole lot better than that just because of the effects of the Earth's atmosphere. And you certainly can't hold a fixed field of view because you're on this moving platform. The Earth is rotating, and it becomes daytime, and then you have to wait until nighttime again, and then you can observe again. Kepler doesn't have that problem. Further, so it doesn't have the effect of the Earth's rotation. It doesn't have the atmosphere in the way. And therefore, it can get down to extremely high precision, down to, in some cases, 50 parts per million, compared to 1,000 parts per million, what you can do from the ground. And with that level of precision, what looks like a Jupiter-sized planet transiting is actually, you get that same signal to noise. Oops, let me back up here. You get the same signal to the noise, the scatter, as you do for a Jupiter-sized planet this size against the sun. You can get it for something that size, which barely shows up at the resolution of this projector. This is a 1.4 Earth radius planet. It has a mass, I think, of about 2.5 Earth masses, orbiting a sun-like star in the Kepler field. And these are the types of planets that Kepler finds everywhere. All of these hot Jupiters and Jupiter-mass planets in eccentric orbits were just the tip of the iceberg. There's orders of magnitude more small planets in the galaxy than there are large planets. There are also really weird things, too, like these binary stars that eclipse each other, like that. You can see their elliptical motion. Oh, and look at that. There's a planet in that system that eclipses both stars. And Kepler found this. Here it is viewed from top down, not quite to scale. The planet is probably about 10 times further away from the center of mass in the system. But the stars are orbiting each other on elliptical orbits. And I forgot the name of the system, but the planet is about the size of Saturn, and it orbits with a period of about a year outside of both of those stars. So you remember the Tatooine sunset in Star Wars? Well, that's the nickname of this particular planetary system. This is Tatooine for real. And you might wonder, how does that happen? How does it move in its nice little stately, almost circular orbit? Well, remember, it's much further away, and so when it looks in from a dynamical perspective, it just sees the total mass in the middle. And the total mass of the binary system is just shifted with respect to the planet's orbit. And you can actually measure the planet's mass because you can see the planet tugging on those stars, causing them to arrive ever so late and ever so early to their eclipses because of the influence of the planet's gravity. So that's pretty cool. Here's another fun system. This was found by a graduate student named Roberto Sanchez Ojeda over at MIT. He found this earlier this year. This is the size of the planet. You have to zoom in. There it is. It's about 1.1 Earth radii. And what's really remarkable about this, well, it's a very bright star. Coupled with Kepler's amazing precision, this Earth-sized planet causes this whopping signal. But look at this. This is one transit, and this is the next transit, and then look at the units. The orbital period is about 8.5 hours. So we thought those were hot Jupiters. Well, this is an extremely hot Earth. It's so hot that you can actually see its irradiated face, and it's so close that it's tidally locked, just like the moon is around the Earth. So it always presents the same face to the star. And that's very hot on one side. And as the planet goes around its orbit, here, as viewed by you, it's new planet, going to crescent planet, going to quarter planet, gibbous planet, full planet, and then it goes away. And you can see it going through that phase progression from new to full planet as the light curve rises. And then it goes behind the star, and it goes away. It was contributing about that much light to the whole system because it's hot. And then it pops back out, and then it goes from full to gibbous to new again. Based on this secondary eclipse depth, you can measure the temperature of the planet. And it's extremely hot. I think it's something like 3,000 Kelvin. It's about half the temperature of the sun. So the short orbital period also opens up an opportunity. Even though this planet is extremely low mass, it's just very small, so it's not going to be tugging on the star very much, there's still a hope, because the orbital period is about the duration of an observing night from the Earth. So within a single night, we could observe the radial velocities of the star and watch a complete cycle go by. And so this was announced at the 50th anniversary in astronomy for Dave Latham, who was one of the Smithsonian Astrophysical Observatory scientists over at the CFA. And we were celebrating his birthday, and then out in the parking lot, we started talking about this system among my colleague at MIT, Josh Wynn, and Roberto, and then my colleagues over in the UC system, Jeff Marcy, and then my collaborator, Andrew Howard at University of Hawaii. And all together, we used Keck Observatory, the 10-meter telescopes at Hawaii. Earlier this year, that's the telescopes I was using primarily. And so we on the California Planet Search team thought, oh, let's measure the mass of an Earth-sized planet. This will be awesome. But then we caught wind that there was another conversation happening at the other end of the parking lot involving Dave Latham and the HARPS team. And HARPS North Spectrometer was built in part by Harvard University. And so we thought we were going to be in competition, and worse for me, I was going to be moving into the office right next to Dave, and here I am going to be competing with him to get these measurements. But fortunately, when I arrived at the CFA, Dave and I immediately had a conversation, and we decided, well, look at this. This is a wonderful opportunity. We're both starting right now. We're both going to finish at about the same time. This is a wonderful opportunity to make the prediction, make two independent sets of measurements, and then immediately have confirmation that we got it right, if we got it right. Or we'll know if we're wrong if we disagree by a large amount. And then we decided, well, since we're investing a huge amount of telescope resources, each night on Keck costs about $100,000. It's comparable over here as well. Since we're both investing a huge amount of resources into this effort, well, we should probably have two separate papers. So we decided that we were going to submit our results to the same issue of Science at the same day, so it would appear in the same issue. And that's what we decided to do. So we went off, each team made their measurements. The HARPS North team in the Canary Islands, we were on the other side of the Earth in Hawaii making our measurements. And we did our whole analysis, and then there was a teleconference, or a Skype meeting actually, that was held. And there was actually a countdown. We went 5, 4, 3, 2, 1, and we hit send on our respective emails. The answers arrived on the other side, and it was gorgeous. Well, here's what we found, first of all. First, this is a spotted star, and we saw that from the light curve. So we knew that there was going to be false radial velocity signals due to star spots rotating in and out of view. Okay, so you imagine the star rotating. One side of the sun, or the star, is approaching you, and one side is receding from you. And since the star is spherical, to first approximation, those will cancel out. But if there's a star spot moving over one face of it, it will reduce the amount of light coming from the side that's coming towards you, and it'll make it like the star is going away from you, and then vice versa. So we fortunately had the Kepler photometry to tell us about the nature of that oscillation, so we fitted that into our model. And here is one night of observations for over one period. It doesn't look like much. Here's another night, another night, another night, another night. There's about $800,000 worth of telescope time right there. And when you take all of those and you phase fold them on the known period, because you have the transit signal, you know the period. I think we knew it to a microsecond based on all of the transits we had seen. We knew the period exactly, so we just folded up the sine curves, and we got this full data set, and you can see that the points are low when they should be low and high when they should be high. And then you can take all of these points and you can bin them just so you can investigate it by eye. So you average them up in bins and phase bins, and you can see there it is. And this amplitude is directly proportional to the mass of the planet. And here's the result. Here these are isodensity curves in a mass versus radius plane for all of the known exoplanets, along with the solar system planets, the green symbols here. And here is that tip of the iceberg that we've been measuring before. And finally, we were down here in the Earth regime. And here is our measurement with its uncertainties. So this is the 1 sigma confidence region for our mass and radius of this planet. And you can see that it falls right along the density of the Earth, maybe a little bit more dense. And when we hit send, we immediately redid this figure and put on the HARPS North team points and science in action. They nailed the bullseye, basically. So there's their measurement compared to our measurement. And then combining the two, we got a factor of square root of 2 better in both of those dimensions. So it's just a wonderful opportunity, and it kind of shows the collaborative spirit that's taking place within the field of exoplanets. It's no longer this very competitive field the way it used to be when there are just a few planets. We now have thousands of planets from the Kepler mission. We have more planets than we have people working on those planets. There's planets just laying around, interesting systems that have not been characterized in 4 years because nobody's gotten to them yet. And that's the new direction that exoplanet is going in. So here's another interesting find. This is something that looks fairly representative for planetary systems throughout the galaxy. This is the Kepler-11 6-planet system. All 6 planets transit the star, which is remarkable, because you need to have a very high degree of mutual alignment among all those orbital planes to get them to transit together. And all of these planets are smaller than the size of Neptune, and all of them orbit with a separation intermediate between Venus and Mercury. So you have an entire solar system crammed within the orbits of our inner planets. And this is something that we see coming out of the Kepler sample over and over and over again, these very compact architectures. Now you might be wondering, then what does that mean for our solar system? Does that tell us that we are common or rare? And for sun-like stars, the verdict is still out on that one, because these are much easier to detect than the more distant planetary systems like our own, with the planets much further away, much less likely to transit, and they transit far less frequently, because it takes an orbital period to get back around. And that's the answer that I used to give whenever I would give talks like this. I would say, well, we don't really know how common the solar system is. But you have to take a Copernican viewpoint. And once you do, you can actually start to address that question. You have to realize that our galaxy is not filled with stars like the sun. This is a beautiful figure showing the distribution of stars that reside within about 30 light years of the sun. Sun-like stars are yellow. Stars more massive than the sun, like Vega and Sirius, are represented here. These are called A-type stars. But the vast majority of stars throughout the galaxy and within the solar neighborhood are these little red dwarf stars. And they have masses and radii ranging from about half the mass of the sun down to about 1/10 the mass and radius of the sun. It is these little red dwarfs that form the majority of stars throughout the galaxy. 7 out of 10 stars in the galaxy are red dwarfs. Now, you wouldn't know that looking up at the night sky. Looking up at the night sky, your view is dominated by these things. But even though they form the minority of stars in the galaxy, it's just that they are very bright, and so they dominate our view of the sky. Furthermore, most of their light is being emitted in wavelengths that our eyes are sensitive to. But if we were to take an infrared view of the sky and switch away from our optical view, we would see a totally different sky. The sky would be covered with these little red dwarfs. So I like to call them the galaxy's silent majority. So there's also a huge advantage using the transit technique for looking at these small stars. They might be faint, but remember the depth of the transit light curve is inversely proportional to the radius of the star squared. So if you go from looking at stars like the sun to stars that are about 1/4 of the sun's radius, then you gain a factor of 16 in transit depth. So that's a huge gain. So what you give up in brightness, you gain back in the depth of the transit. You get signal to noise. Furthermore, if you're interested in planets that are orbiting within the habitable zone, well, let me get to that in just a second. Actually, I just remembered I wanted to tell you about the MERTH survey. This is led by Professor Dave Charbonneau over in astronomy, and he was on this idea even before the Kepler mission. And to attack this problem, they actually do ground-based observations, but they use these amateur-class telescopes. These are little 40-centimeter amateur telescopes that you can buy online, basically, and have delivered overnight if you'd like. And they have a little army of them. I have 8 total in Arizona, and they're fully robotic. So once the sun goes down, the dome slides open. The telescopes then point to the sky, and they run through their little calibrations, and then they start walking down their little target lists. And what they're doing is they're just moving from one red dwarf to another red dwarf, taking brightness measurements over and over and over again, similar to what Kepler does. And here's one of the planets that was discovered by the MERTH transit survey, and you can see again this huge amplification of signal to noise. This is a planet called GJ1214b compared to a planet called Corot 7b. Both planets are identical in size, but here's the transit depth for GJ1214 compared to the transit depth for Corot 7. Huge gain. Now here's one of the little red dwarfs that was in Kepler's field of view. This is a star called Kepler Object of Interest 961. It has since been renamed as Kepler 42. I don't know which one is more romantic. And it doesn't look like much. This transit light curve is really phenomenal, but it doesn't look like much. There's a lot of scatter because the star is pretty faint. The transit signal is not that deep. We actually had to try a variety of models to try to just make sure that we were actually seeing something there. But what it shows, based on the depth and the size of that tiny little star, which is about 1/5 the radius of the sun, is actually this planet right here, and that's the Earth. So this is was at the time the smallest exoplanet that had ever been discovered. This is Kepler 42d. It has a radius about comparable to that of Mars, and it's in a 10.8-hour orbit around a little red dwarf star. Moving outwards, this one has an orbital period of about 1.2 days, and the third planet in the system has an orbital period, this is about 1.2 days, and this one's about 1.8 days. Oh, and they're not habitable. Sorry. They probably have solid surfaces, but water wouldn't probably exist in a liquid form, even if they had atmospheres, which we don't know. But what is really interesting, going back to the Galilean satellites, is that when we wanted to issue this press release announcing this new planetary system, we wanted to show it to scale compared to maybe the first hot Jupiter that had ever been found. But it didn't fit onto that scale. You couldn't even see it. Because the star is only about 70% bigger than Jupiter, and the orbits of the planets are comparable to the orbits of the Galilean satellites around Jupiter. So what we have here is a system of planets around a star that is about the same size as a planet in our solar system and its moons, which is really cool. So this gives you that broader galactic perspective of planetary systems. Another one that we found is Kepler 32, and it again has this very compact architecture with periods ranging from 0.7 days out to about 23 days, and planet sizes going down from a little bit less than the Earth up to the size of Neptune. And this, right here, I argue, is kind of the standard outcome of planet formation throughout the galaxy. This is what planetary systems look like galaxy-wide. Little compact systems of sub-Neptune-sized planets in orbit around a little red dwarf star. And when you start realizing that stars like this form the majority of the entire galaxy, stellar population, and that stars like this have about 1.5 planets per star throughout the galaxy, you start realizing that these types of systems by number absolutely dwarf solar systems like our own. And then you start staying up late at night wondering, what am I doing laying awake in my bed on an Earth-sized planet at 1 astronomical unit from a G-type dwarf star? I should be around a red dwarf somewhere. So I was about to tell you earlier about the habitable zone. This is just a rough concept that basically is a zone of roughly constant equilibrium temperature or a constant range of equilibrium temperature. where a planet could conceivably have liquid water on its surface. I like to use this term very loosely with a big grain of salt because there are tons of factors that go into habitability on a planet. And it's really important to also note that we don't really even understand the conditions for habitability on our own planet. We don't understand abiogenesis on our own planet. So we don't really know that even if a planet lies within the zone, it will be inhabited. But at least it's step one. And we are very interested in finding that step one, lots of planets in their habitable zones. And the habitable zone around a red dwarf is in much closer. And this affords a lot of other opportunities. In addition to having a deeper transit depth for the same size planet, the orbital period is much shorter, so you get to see many more transit events go by per observing season. And the transit probability is much larger the closer you are to the star. So all of these factors give you big gains in looking for habitable zone planets around red dwarf stars. And a graduate student here at the CFA named Courtney Dressing conducted a study last year along with Dave Charbonneau, and they're updating this study by looking at all of the red dwarfs in the Kepler sample and then basically counting up on a per star basis. Each one of these little blue streaks here represents the habitable zone of each one of these stars and planets. And they just basically count up what fraction of all of those planets, corrected for transit probability and detection probability and things like that, what fraction of the planets lie within the star's habitable zones. And the answer that they found is really remarkable. There are about 0.56 Earth-sized planets per habitable zone around red dwarf stars. So if you're looking at a red dwarf, flip a coin. If it comes up heads, about the same probability of coming up heads is the probability that it has an Earth-sized planet in its habitable zone. That's amazing. So if you're really interested in the search for life outside of our solar system, the odds just swung in our favor, right? If the answer had come back 0.01 planets per habitable zone, we might have reason to dismay. But I would argue that this number gives us lots of hope, lots of reason for optimism. Let's see here. All right, so those are the two techniques that I use most heavily, the radial velocity or Doppler wobble technique and the transit technique. I'm going to show you two more techniques. This is a fun one, known as gravitational microlensing. First, we'll start with Einstein, who came up with the special theory of relativity. And it was special because it was concerned with the nature of motion and the interaction and the way matter moves with respect to light within basically a non-accelerating reference frame. He generalized this for an accelerating reference frame, for example, in a gravitational field, and then he came up with his general theory of relativity. And within that theory, he posited that massive objects warp space-time around them. By virtue of having mass, we're all warping space-time right now. This is important because if you're looking towards a star very far away in the galaxy, it is shining in all directions, isotropically, and only a few of those directions actually correspond to our line of sight. However, if you place a massive object here, it will warp space-time around it along that line of sight. And it will cause light that would have otherwise missed our eyes to then be bent and go into our telescopes. And this causes two little images of the background star to appear on either side of that massive object. It serves as a lens. And it actually magnifies the brightness of that background star. So what you have here is a lens star, a source star. The lens star, you don't even have to see it, but its gravitational field will magnify the light from the background star. This happens for galaxies, lensing very distant galaxies in their background. And when they're perfectly aligned, you get a feature known as the Einstein ring. This corresponds to almost perfect alignment between those two bodies. If they're slightly misaligned, then that ring goes into two small images. So here we have that foreground lens star moving in front. No, I'm sorry. Here's the background source star. And coming back around again, here's that red. Actually, I'm sorry about this. Let me see. Yes, this is the background star here. And so they're just moving with respect to each other because stars drift with respect to one another in the galaxy. And as these two stars approach, you see the lensed image of this source star form those two blue images. And if we come down here to the magnification plot, this is basically the amount of light that you're seeing from both stars. And this is the lensed images growing in brightness and then fading back down again as the two stars pass each other in the night. And this happens by chance throughout the galaxy. If you look at enough stars, then you give yourself a chance to see this happen. This is kind of fun because it allows you to see very distant background stars that you normally wouldn't be able to measure their spectrum, for example. So astronomers like to use this technique to study stars on the other side of the galaxy while using foreground stars to lens them and make their telescopes effectively larger. That's one way to do it. However, if the foreground lensing star has a planet, this purple dot up here, at a distance corresponding to its Einstein ring radius, then something pretty cool happens. What you get is the image, the lensed image, will eventually cross the position of, or near the position of the planet. And the planet's gravitational field lenses the lensed image of the background star, causing this secondary brightening in the light curve. So it's going to go up, turn over, secondary spike, and there's your planet. And you think, what are the chances of that? Well, the people that do these surveys look at hundreds of millions of stars throughout the year. And what they do is, or at least the initial technique that they use, is they would make about one brightness measurement per night for those hundreds of millions of stars, because they had to move from different fields and their telescopes had a limited field of view, so you have to hop around to different fields. But once they started sensing that the light curve was going up, what they did is they started sending alerts out to their little network of amateur observers. And the amateur observers would take out their little amateur telescopes, small to medium-sized telescopes, and aim them at that one particular star and start making brightness measurements of their own. And then there also would be other professional class telescopes that would get on the action, and you start getting a very dense time series of brightness measurements. And that allows them to catch that very short, very brief one-time rebrightening event that happened over here. And so for every one of these high magnification events, it would trigger, zero in on it, pound away at it, most of the time nothing. But in this particular case, they caught an Earth-sized planet orbiting at a few astronomical units from its star. And that tiny planet would not have been detectable using the radial velocity or Doppler wobble technique, and it wouldn't be likely to transit its star because of the very low transit cross-section. So this gives you a very complementary method of studying the occurrence rate of small planets throughout the galaxy. And the numbers of planets that they're finding around stars throughout the galaxy with this technique is very much consistent with what Kepler is seeing very close in. And so that boosts that 1.5 planets per star to something like maybe 3 or 4 planets per star throughout the galaxy. The final technique is just going out and directly taking pictures of planets. This harkens back to the old days when you just look up in the sky and there's a planet. Well, it's a lot harder when you're looking around other stars. It's a problem of both contrast and angular resolution. The further away two objects get, the more and more they look like one object. So that's resolution. If you can gain more resolution, you can separate those two objects apart. The other problem is that planets are much fainter than stars, so it's difficult to see their feeble light, which contributes only about 1 photon per million or 10 million photons from the central star. So it's very difficult. However, if you use a large enough telescope, you can gain resolution. That's simply through understanding that telescopes are Fourier transform machines, essentially. This is the aperture of a telescope seen in cross-section. I'm just going to show it in one dimension just to make it a little easier. Plane parallel wavefronts from the electromagnetic field emitted by the star are incident upon that mirror and caused a top hat distribution of intensity across that diameter. The Fourier transform of that top hat distribution gives you a sinc function, or at least when you take the power and square it. And then if you go back out into a two-dimensional image of the intensity from that, you get what's called an Airy pattern. And the distance from the center to that null is what sets the resolution of the telescope. The bigger the telescope, the smaller that Airy pattern. The smaller the telescope, the bigger that Airy pattern. And that's why we like to use big telescopes. However, the Earth's atmosphere is a big problem. This is what a star looks like when you take a picture with a very large telescope. All of that resolution is kind of wasted because the Earth's atmosphere blurs out the image. However, if you can sense the non-parallel nature of that wavefront, you can send corrections to an adaptive mirror that can adjust its shape to take on the kind of conjugate waveform and then send out corrected wavefronts to your detector. And so you can use adaptive optics to sharpen that image and remove the effects of the Earth's atmosphere. And using that technique, along with a couple other neat high contrast techniques, this is an example of an imaged planetary system. These are 4 giant planets in orbit around a nearby A-type star called HR 8799. And it's Jupiter-sized planets, a little family of them. And you can actually sense orbital motion for this system. And here's another example of a very young star with a young planet right next to it. This is Beta Pictoris b. Those are actual photons received from a distant planet. So I covered a lot of techniques, and I showed you how we find planets using the 4 major techniques: the wobble, transit, gravitational microlensing, and direct imaging. The take-home points from this, those are the techniques, and that we are completing the Copernican revolution. There are more planets than stars in the galaxy. There's of order 100 billion planets out there in the galaxy waiting to be discovered. The most common type of planetary system is a compact system of sub-Neptune-sized planets around a red dwarf star. The night sky is full of other suns, and the next step is to reach out and find those planets that we now know are there. So we're moving forward with this revolution. You can learn more about all of this by finding this video that I did in collaboration with Jorge Cham of PhD Comics. You can search for Exoplanets Explained on YouTube and watch a little 8-minute video explaining all those techniques you just heard about. And I thank you and take your questions.
Thank you very much, Professor Johnson. We're now going to open up questions. So there are microphones here.
No? Do you need to use the microphone? Or, oh. Yeah.
I have a question about the using gravitational resonance for these planets.
Mm-hmm.
You kind of said like, well, it like initially it seems like it doesn't happen very often. But like, how often does it happen, and do we detect it to be able to say something significant about how many planets we expect are out at large radii?
Okay.
Like, is that still developing, or
Yeah.
do we already have enough data?
No,
So the first generation systems use these telescopes that had fairly narrow fields of view. So you could only fit, maybe only 10 million stars per telescope pointing. So to build up to hundreds of millions of stars, you had to do multiple telescope pointings per night. And then there's always a chance you're going to miss something while you're going through that process. And so the next generation of telescopes are taking advantage of basically Moore's law growth of the size of CCDs and how fast you can read them out and things like that, coupled with large field of view telescopes that are dedicated for the purpose of imaging millions and millions of stars at the same time. So the detection rates are increasing all the time. And this need to do the kind of amateur telescope follow-up or use other telescopes to do the follow-up work is going away, because with these huge detectors that can be read out very quickly on large telescopes with huge fields of view, then you can almost just basically do that follow-up yourself. You're just sitting on the field taking images every 10 minutes. And so there's a network of 1.6 meter telescopes, 3 of them that are in the southern sky, and they're distributed in longitude in South Africa, Chile, and I think over in Australia. And so it's always nighttime somewhere on that telescope network. And so they just get continuous coverage down there. And so that next generation telescope system goes up in a couple of years, and I think they're going to get thousands of events per year, something like that. Just the lensing events, and then of those, some fraction will be planetary events. And you can do quite good statistics, just because you're just catching everything that's up there. If there's a planet near the Einstein ring radius, and that planet and that star and planet system pass in front of the star, then you can start just counting up the number of stars that are out there and start getting a sense for how many planets are out there. Yes?
What do you think the best application is for direct imaging? Because, like, is it something that's been...
I think it's being recorded, so they want your question.
Oh, okay. Yeah, so for direct imaging, is it best, like, is it becoming more and more popular, like a better method, or is it something you'd use as like a follow-up if you know where something is and you want more information?
It's yes and yes. It's for both of those. So the systems are getting more and more sensitive. Their wavefront correction systems for the AO systems are getting better. The high contrast imaging techniques are getting better. And there's systems that are being designed and deployed that are specifically built to do this. All of those previous systems I showed you used existing adaptive optics systems that were multi-purpose instruments. Now they have purpose-built adaptive optics systems just for looking for planets. It's really the regime of use is for young planets that have just been born, and when they're born, they're hot and still contracting, and they radiate a lot. And so it's best at detecting those inflated, hot, young planets than it is for detecting cold planets. However, if you are observing a star's radial velocity in time and you see kind of an upward slope of the velocities, you're just seeing an almost nearly constant acceleration of the star. And that could be just kind of the Taylor series component of a long Keplerian that's way longer than your time baseline. And we've actually been using that as a telltale marker that there's something massive and widely separated from its star. And we've been zeroing in on those radial velocity trend systems to specifically try to image those planets.
Thank you.
With respect to the gravitational microlensing thing, so if you detect a spike in the sort of bell curve shape, isn't there a limit to the information you can glean from that aside from the fact that a planet does exist? Because intuitively it seems to me that you couldn't judge how far radially it lies as well as the mass at like the same time, because either one of those could factor into the spike, right?
Well, actually, for certain configurations, you will get a decrement in light. So the exact nature of that curve, I showed you a particularly simple curve. It was just a simple spike up, but you can get a deflection down and then back up and then a wiggle down.
Okay.
And that exact way that it crosses the so-called caustic or near the Einstein ring gives you a lot of information. And as a matter of fact, that time that you saw that secondary little blip was a couple of days. Okay. And that's a decent fraction of the orbital period, actually. So you can detect the change of the light curve as the planet is moving around its star. So you can actually sense orbital elements as well. So there's a lot of details hidden in that little light curve that give you the exact separation, at least projected on the sky and relative to the mass of the central star. So then once you have the mass of the star and maybe a distance to it, then you can get those parameters absolutely.
Okay, so would it be like the amplitude is related to the mass, and then it seems to me like the time
and
that it
the
takes
separation
would be related to the radius?
Yeah.
Possibly?
Yeah, there's combinations of both mass and separation in both of those effects.
All right.
Yeah.
Anyone else?
Have we been able to detect any moons around any of the exoplanets as well, or or are our current technologies still not advanced enough to get that kind of resolution?
There's one person here at Harvard at the CFA named David Kipping, and he's a postdoctoral researcher. He's going through the Kepler data very meticulously, looking for evidence of moon transits. Because you can imagine you have the moon leading the planet, you'll get a tiny dip first, and then the planet comes on, and then you'll have a slight rebrightening as the moon moves off, and then as the planet moves off the stellar disk. And so he's put a lot of careful thought into the exact nature of the light curve for various moon configurations. But the problem is that because that moon can be pretty much anywhere in orbit, and those lead to very different light curves that are not necessarily periodic. One transit is leading, the next transit is trailing, the next transit is superimposed. It's very difficult to build up the signal necessary to see it. But he's looked through the brightest examples of the brightest Kepler stars where they have the highest signal to noise. And I think he's checking and rechecking, but so far he hasn't found any evidence of moons just yet. Yeah.
For the microlensing technique you were talking about, I have two questions. The first one is how magnified will that make the background star? And also, what is the potential for possibly seeing a star which is lensed by a star in front of it, but which is also lensing one behind it? You get like a triple, which
Okay.
is really unlikely, but like, what is the possibility? What would that be able to do?
So the chance that a star is being lensed at any given moment in the galaxy is about 1 in a million. And so the chance that you're going to see a double lens event is going to be 1 over a million squared. So it's pretty unlikely that that would happen. If it did happen, you might see that same effect that you're seeing for the planet serving as a secondary lens of the lensed image. And so you would have some lensed image that might pass within the Einstein ring radius of another star, and then that gets further lensed, and it would just get brighter again. For the high magnification events, the magnification is of order 100. But for that depends on the cross section or the impact parameter, how close those two stars are on the sky. The closer they are, the higher the magnification. And so the further away you move, you get shallower and shallower magnification events.
All right, thanks.
One more?
For the direct magnification, you talked about the adaptive optics being used for the mirror. Is it the case that normally the kind of modifications or the compensations for atmospheric events occur on the actual mirror itself, or are sometimes they applied later to the data that is collected?
Neither, actually. I'm sorry, I gave a pretty simplified view. It's not actually, sometimes we can make small or large frequency modifications to the actual gigantic mirror. So the Magellan telescopes that Harvard has a share of actually have active optics that push and pull on the underside of the mirror to adjust it. But to get the really fine, high-frequency corrections, you actually need to take the telescope pupil and then re-image it onto a smaller mirror down further in your optical path. And those range in size from maybe about the size of a dime to about the size of a dinner plate, depending on the nature of the system. Well, if there's no more questions, thank you very much.